Continuing on the theory of spectroscopy, I think it's important for us to talk a little bit, about physical chemistry, especially, quantum chemistry, because that's the basis of spectroscopy. Now, for light to be absorbed by a molecule, you need the energy that is incoming from, the light to be equivalent to the energy gap, between the electronic states, where the electron transition is gonna take place. And so the energy of the radiation being absorbed, needs to correspond, to that energy gap where the electronic transition is gonna happen. Now, remember, every molecule, has got three different states. You've got the electronic states, you've got the vibrational states, that are in an electronic state. And in every vibrational state, you've got a rotational state as well. Meaning, if at all you've got a molecule, again, you've got, say, if at all I can illustrate this, you've got an electronic, maybe that's a ground level, and for every electronic state, you've got vibrational states as well, and of course there are different levels of vibrational states. And for every vibrational state, you've got rotational states as well. But that's the case, for molecules. However, for atoms, you do not have vibrational states, you do not have rotational states, and as such, for atoms, all what you have, are electronic states, so you do not have rotational and vibrational states, meaning the transitions that are possible for atoms, are fairly simple, because you've got very discrete, electronic states, and you do not have vibrational and rotational states. And that's gonna explain, in the next slide, why when you talk, if at all you're dealing, with an atomic spectra, the results, coming from electronic transition with atoms, you've got a very well defined, almost what you refer to as a line spectra. So that is the case for atoms, in this case, say, sodium vapor. However, when you're talking about, say, benzene vapor, which of course is a molecule, now you can see the absorption spectra that you're getting, it's not really a line spectra, but it's got a lot more character to it. And the question is, why does it have a lot more character compared, say, to sodium vapor? And the reason for it is, like I said, sodium, being an atom, it does not have rotational and vibrational states, and that's why you have a very simple, type of spectra. Benzene, on the other hand, is a combination of different carbon bonds bound together. And for that reason, the electronic structure is a bit more complicated. And so you can have electronic transitions, taking place, between the electronic levels, as well as, between the rotational and vibrational levels. And that's why you've got, a much more complex spectrum. Now, if at all you've got benzene now in hexane, meaning it's dissolved in a solvent, of course, you're going to have, the solvent equally participating, in the absorption of light, that is taking place. And because equally hexane is a molecule, you've got all these electronics slash vibrational and rotational states. That means you've got, a lot of possible probability of transitions, that would be taking place. And for that reason, you've got a lot more complex or broad spectra, because of all those possible transitions. That's important. Because if at all you're given two types of, spectra, you can actually tell, is it an atomic, kind of, spectroscopy? You can tell because it needs to be a line spectra. If at all you've got benzene, say, in vapor, you don't have a solvent. Again, you don't have a very complex spectra. So you can tell the number of, atoms, that participate possibly in that transition. Now, on the other hand, look at biphenyl, which are two benzene rings, really fused together. Now you can see the kind of spectra that you are getting, now is less characteristic. It's very, very broadened, because there's so many possible transitions, that will be taking place, because of this complexity, of molecules, or rather of atoms, that make up the biphenyl compound. And so you can tell then for absorption spectra, the more complex or bigger the molecule gets, the less defined, the absorption spectra is going to be. It's going to be very, very broad, because of all those possible transitions, that would be taking place. I should emphasize the following. When a molecule absorbs a photon, it gets excited, to a higher energy level. And of course, we know molecules or atoms do not prefer to stay in an excited state, and they like to release the energy very, very quickly. And so the energy gets released, so that the molecule can be stabilized, at the ground state, and it releases a photon. And a photon, when it's released, that's the basis actually of emission spectroscopy that we're going to talk about very shortly. But in general, you also release heat as well. Now, light that is emitted typically comes, from electronic transitions. So when the electrons are falling, from an excited electronic state, to the ground electronic states, that's when you get a photon. However, because you also have rotational and vibrational states, the electron can be relaxing in the vibrational state, and when it's relaxing in the vibrational state, it generates heat instead, okay? And so electronic state, relaxation really gives off light. Vibrational relaxation gives off heat. So what is this all good for? What I'm trying to explain here is the basis, of possibly 3-4 different types of spectroscopic techniques. I've sort of already mentioned the absorption spectroscopy. But also, when there is absorption, there is excitation. And what results after, is emission of light, like I've tried to explain. And emission of light, is the basis of the other types of spectroscopy called emission spectroscopy. And of course, there are different types of emission spectroscopies, that we're going to mention, like fluorescence, phosphorescence, and luminescence as well, sort of is an example, of an emission spectroscopy as well. But also scattering, remember, can happen based on Raman scattering or even turbidimetry and nepherometry as well. Remember, for all these types of spectroscopies, it's important because they are all dealing with a photon, impinging on a molecule or an atom. It needs to have a linear relationship, to the concentration, which is what you are interested in. For example, if at all I'm doing absorption spectroscopy, we know the relationship, is equals to molar absorptivity multiplied by path length multiplied by concentration. But we know that absorption really is also equals to the negative log, of transmittance. And transmittance, we know, is equals to, the power of the light, that is detected, or the power of the transmitted light, divided by the power of the incident beam. And that is what I have down here. So you can see that relationship that I need to relate transmittance, to absorbance. And I need to relate, absorbance, to concentration, which is what I'm interested in. And so those relationships, mathematical relationships, of course, need to be known for these spectroscopic techniques to be really useful as an analytical tool. So let me quickly talk about, or remind you really about absorption spectroscopy, which is what you guys have done. In the lab, I think you guys have done AAS, atomic absorption spectroscopy, and the basis of it, of course, is a theory we are talking about. But you've also talked about or done spectrophotometry, especially when you guys were trying to determine, the concentration of polyphenols in tea and in coffee, in the last lab. And you can see that the basis of it in terms of the theory, like I've tried to mention, that absorbance is equals to the negative log of transmittance and is equals to the molar absorptivity, multiplied by the path length, multiplied by the concentration. It's important for us to remember what are the factors, that affect the sensitivity of molecular and atomic, absorbance spectroscopy, so that you know when you're doing it in the lab, what you need to optimize and so on. And this is a review because you guys have already done it, in the lab. Now, absorbance spectroscopy, is always based, on Bayes' law. And of course, Bayes' law, refers to, that relationship. Now, however, Bayes' law, it's only effective, when you're dealing only with dilute concentrations. Meaning, if the concentrations are not dilute, meaning absorbance, if it is greater, than 1, then Bayes' law does not hold true. All right. So Bayes' law, or this relationship that is the basis of absorption spectroscopy, only works, for very dilute solutions where absorbance, is less than 1. And the reason for that, because for very concentrated solutions, now, you get the atoms, or rather the molecules, interacting, with the other molecules, creating sometimes dimers and so on, dimers. All right. And sometimes you can have molecules, interacting with each other, due to hydrogen bonding, or sometimes, due to van der Waals forces. If at all, is a fairly hydrophobic, type of a molecule. Now, dimers, compared, say, to the analyte, have got very different, molar absorptivities. It's almost like, you've got two different types of chemical species. And so that's why you need, to have a dilute solution so that you discourage, the solution from forming dimers or interacting to form hydrogen bonds and that kind of thing, that affects, the molar absorptivity, of the analyte. Now, it's also important to remember, that the Bayes' law also gets affected, by other chemical limitations other than the concentration. And often, that when an analyte is undergoing chemical equilibrium, if an analyte is undergoing chemical equilibrium, then Bayes' law would not hold true. I'll give you an example. Assume you're analyzing aspirin in the lab, which is, I guess, acetyl salicylic acid. Let me symbolize it, with HA. It's an acid. It's a monoprotic acid. And we know all monoprotic acids, or all weak acids in general, undergo dissociation, to give you the conjugate base, and then the proton or the hydronium ion is generated, and the equilibrium, constant is what you call the Ka. Meaning, if at all I take acetyl salicylic acid or aspirin and dissolve it in water, it is not gonna exist, as acetyl salicylic acid. Instead, it's gonna dissociate, into its conjugate base. And of course, a portion of it is still gonna remain as HA, depending on the magnitude, of the Ka. And of course, we talked a lot about that, in Chem 211, as well as, of course, Chem 102. That's the basis of it. So meaning, of course, the molar absorptivity, of the conjugate base is very different from the molar absorptivity, of the conjugate acid. And as such, now you've got two species, that are actually interfering. And so for that reason, now we got a problem. And so if at all you've got a chemical species that undergoes chemical equilibrium, then remember again, that the Bayes law, is not gonna hold true. And so you may ask, what's the solution then to this? And because most of the compounds that you guys are going to be working with in the lab are possibly acids or weak bases. The solution to this problem is, of course, you buffer the system. Okay, make sure you add a buffer, so that you do not have that kind of, equilibrium transition, or at least, it's constant. The equilibrium transition, is constant, for standards, as well as the analyte. So take note of those things, that are very, very important, because they completely affect, your results, for absorbance spectroscopy, when you're dealing with those types of situations. So you need, of course, a dilute concentration absorbance less than 1 anytime you're doing you're doing absorption spectroscopy. And you guys remember that's why if at all the absorbance was greater than 1, we had to do a dilution. You had to dilute the sample for us to be able to use this type of technique. Now, other than chemical limitations, of course, you also have, instrumental limitations, that actually affect the result, for absorption spectroscopy. For example, the wavelength, that you choose, the wavelength that you choose to use for your absorbance spectroscopy very significantly, of course, affect, the sensitivity. So ideally, you would be looking, for the wavelength at which you get maximum absorbance, all right? Something like this, okay? So in that case, then you're gonna see, and that's absorbance, that's a concentration, and that's a concentration. And so you're gonna see, this one you get a lot higher slope compared, say, to this one, where you get, less slope. And so ideally, we should be using the wavelength that we are getting the maximum absorbance. However, in the event, that you do not want to dilute your samples, assume you're getting an absorbance, say, of 2, okay, at the wavelength of maximum absorbance. You can also decide, to have a shortcut such that, instead of diluting the samples, you can decide, to use another wavelength, that you're not getting the maximum absorbance, but nonetheless, you're getting an absorbance as well. And so that one is gonna help you not dilute the samples, and equally, of course, you're gonna have a linear relationship. So that's the other approach, that you can use if at all you do not want, to dilute the sample. The challenge with that, of course, you'll be affecting your sensitivity, because sensitivity is greatest, at the wavelength of maximum absorbance. So another instrumental problem, that we face when we are dealing with absorption spectroscopy is scattering. Ideally, of course, we do not want light to be scattered. We want light to be absorbed, all right? So scattering is another problem. And sometimes we refer to that, as stray light, as stray radiation. Stray radiation, can result, obviously, from particles, or dust on the cuvette, scattering, some of the light. But you can also have, stray radiation, that is coming from, the bulbs or the lighting in the room. And so the lighting in the room is gonna impact, of course, the analytical, radiation of transmittance and the incident beam, and you can see that it's gonna affect your absorbance that is generated. So stray radiation either coming from the lighting in the room, or also due to the scattering from the dust particles that are present on the cuvette, could be another impact, to the sensitivity of your absorbance spectroscopy. Now, it's important, for us, to really understand at the molecular or electronic level what's exactly happening, when absorption of light is taking place, within the analyte. Remember, not all analytes, whether organic or inorganic, are gonna absorb light. So exactly, what determines what types of analytes absorb and what types of analytes do not absorb. For example, I think we all know hexane, for example, is not colored. And the reason it's not colored is because, it's not absorbing really any of the light, in the visible radiation. It's not absorbing any of your white light. It's not absorbing any of your white light. And that is why it's not colored. Because remember, the color, typically comes from, the absorption of part of the white light. And then, of course, whatever is not absorbed is what you actually see, as the color. So hexane really is not absorbing any of your visible light. Why is that? I think you remember in Chem 1 or 2, there's what you referred to as allowable transitions. Remember, if you absorb light, what's happening is electrons are being are transiting, or they're being excited, from the lowest energy level. Of course, often these are the bonding electrons. The bonding electrons are being excited, from an electronic state in the ground level to a higher energy level. Now, meaning if a taller molecule, doesn't have, for example, the non-bonding electrons, okay, it means it's likely, that the energy gap, between, of course, remember the way it's organized, the energy, the molecular orbital diagram is organized like this, meaning the bottom of it, would be the sigma electrons, this one is gonna be the higher, slightly higher energy would be the pi electrons, and then after that you've got the non-bonding electrons, and then next to it, it's gonna be, the pi star, the anti-bonding electrons, and then you're gonna have, the sigma star. Meaning, if at all I've got non-bonding electrons here, it's very easy for them, to transition, to the pi star, because the energy gap, the amount of energy that is needed, is very, very small. Similarly, if at all I've got, pi electrons, the case for any unsaturation in the compound, it's fairly easy, to transition from here, to the pi star again. The energy gap, is not very, very large. On the other hand, in the case of hexane, I've got just the sigma electrons. It's very difficult, for them to transition, from the sigma molecular orbital all the way, to the pi star. Reason being, or rather to the sigma star, reason being, it's a huge energy gap, meaning, that transition is not favored, because it's got a lot of energy that it needs. And that's the reason, why some of these analytes do not absorb, because the transitions or the energy gap, that's available is so large, such that, you wouldn't be able to get light that has got enough energy to cause that kind of transition. So take note of this then. If at all I've got an alkene, for example, it's got a double bond, meaning it's got, pi electrons, meaning it's fairly easy for it, to be excited, those electrons, to the pi star, and as such, you're gonna have light, that is generated. Or meaning those kinds of compounds are gonna absorb because of that allowable transition. Look at the carbonyl compounds. Again, you're gonna see with the carbonyl compounds, they've got non-bonding electrons. Oxygen has got a lone pair of electrons, and so it's very, very easy, to cause that transition, from non-bonding electrons, to the pi star, meaning almost all carbonyl compounds absorb, radiation, meaning they are good candidates, to use for absorption spectroscopy. Take a look, at something, like the azo compounds. Again, nitrogen has got a lone pair of electrons, meaning that types of transition, from non-bonding to the pi star, is possible, meaning it's very, very easy, again, to cause light to be absorbed. And so that's why you would see, if at all you've got compounds that are conjugated, meaning, they got lots of bonds like that, they've got lots of double bonds, you'll see that these compounds are very colored. For example, lycopene. If you look at the lycopene, it's got a lot of, conjugation, from the double bonds. And so that's why it's very, very colored, because the likelihood, of the pi to the pi star transition is very, very high. If at all, again, you've got something like, olive oil. Olive oil is an unsaturated oil. Again, you're going to see it. There's a lot of color in olive oil, because of those possible transitions. So it's very important for you to understand what's happening at an electronic level, for you to see these things in real life. Now, other than organics, which is what I've talked about here in terms of electronic transitions, we also know some of the inorganics, also are colored, or support, light from being absorbed. So exactly what's happening then, at an electronic level. Now, of course, we know organics, have got electrons either in the s orbital, in the p orbital, in the d orbital, and so on. And you're going to see, that all transition matters, tend to have, unfilled d orbitals, meaning electrons can transition, between the unfilled d orbitals. And so because of that, that energy is favored. And for that reason, there will be some molar absorptivity, meaning those types of inorganics, things like iron, things like chromium, things like cadmium, and so on, they are colored. And the reason they are colored, is because, they've got allowable transitions due to their unfilled d orbitals, and so that transition, is actually possible. Meaning that you can actually do absorption spectroscopy of transition matters, easily, because you've got they absorb light, and they absorb light, because of that allowable transition within the unfilled d orbitals. Having said that, though, you're gonna see that, the sensitivity, is very, very low if at all you just try to analyze inorganics without chelating them, without adding a ligand to them. Because you can see, the molar absorptivity is very, very low, okay? And if at all, the absorbance, again, is totally dependent, linearly proportional, to the molar absorptivity. So you want a very high molar absorptivity for us to have a very high absorption. And so to increase, the sensitivity, typically, we would chelate, these inorganic, with a ligand. And you guys have done this before, possibly, with the iron, like those of you who did Chem 211, iron 2 plus. I think you tried to do the analysis of iron in water, but instead of analyzing it, on its own, though it's colored, instead you reacted it with a bipyridine complex, so that now you've got a lot of molecule, in the complex. And so there's lots of possible transitions, and so that increases the molar absorptivity. Now you can see, to something like 10,000, and so that increases again, the absorbance, meaning the sensitivity really increases. So even though you can do inorganics, especially the transition matters, without necessarily adding a ligand, the sensitivity is low, and as such, you need to complex them, using an appropriate ligand so that you can increase, the molar absorptivity, and then such, increase, the absorbance. So in the next lecture, we're going to talk about the components now of building spectroscopic techniques, and how each of these components, impact sensitivity and to some extent, selectivity as well.